bit of an idiot.
Oh, you should get more credit for what? The conversion?
Yeah.
Oh, if you missed the conversion and you got any points, consider yourself lucky. At this point, you should have perfect conversion. You can cry afterwards, and I can. If you cry enough, maybe I'll give you points. All right, so let's go through this thing. All right.
Oh,
Did you?
did you get the whole world question right?
Yeah. But I didn't do it right.
He took his exam several days after other people did. Decided that the world revolves on his time frame. All right, so number one, I just give you somebody else's extra piece. Oh, this is the quiz. Everybody sign it? And did Katie? Okay.
Yep.
All right. So what is POSIX and why do we need it? So it's our Unix standard for bringing together a standard API for talking to the operating system. Something along those lines. I think everybody got that one right. All right. 2, convert AB13 from hex into octal. AB13, 16 to 8. All right. This was still heavily missed. You guys can't be missing these. All right. So good rule of thumb, first thing to do is you can convert this. Well, there's a couple different ways you can do this. Typically, the least chance of error for many of you is going to be converting it to decimal first, then converting it into octal. You could also convert this into binary, and then convert the binary into octal, because you can go from hex to binary pretty quickly, and then from binary back into octal pretty quickly. So that's probably the quickest way of doing it, but let's do the full conversion. So we're going to do hex into decimal first. So AB13 into decimal. So AB13, let's put some spacing in here. This is the ones place. This is the 16s place. This is the 256 place. 16 times 16, and then 4096. All right, and A is actually a 10, B is actually an 11. So this guy is 10 times 4096 plus 11 times 256 plus 1 times 16 plus 3 times 1. Oh.
It's 43,795.
43,795. 43,795. Okay, so that is the decimal value of that, right? Base 10. So now we want to convert that into base 8. We do that by dividing it by 8 over and over and over again, recording the remainders. Okay, so 43.95 divided by, or 437.95 divided by 8. 43,795 divided by 8. So 54.74, you said remainder 2?
43.
All right, now I don't believe you. 54.74. 54.74 times 8, huh? It's 3? All right. So that's a remainder of 3. So 54.74 times 8 will give you a number that's 3 less than this number. So that's your remainder 3. 54.74 divided by 8 is 684. Remainder what? 2? 684 divided by 8 is 85. Remainder 4. 85 divided by 8, 10. Remainder 5. 10 divided by 8 is 1. Remainder 2. 2 divided by 8, or 1 divided by 8 is 0. Remainder 1. Final answer is 1, 2, 5, 4, 2, 3. All right. So let's look at an alternative way of doing this. We can turn this number into binary first. So I'm just going to do this on another slide, actually. See where you screwed up?
Yeah, I got another remainder written down wrong.
Good?
Yeah.
All right. So let's look at an alternative way of doing this. All right. So first we're going to take AB13 and turn that into binary. So I'm going to say 10, 11, 1, 3. So we're going to do this in 4-bit binary chunks. So that's 8. That's the 10. That's the 11. That's the 1. That's the 3. So is this the binary version of AB13? All right. So now, put this all together. And now you turn it into 3-bit chunks. This first one is 1. Second one is 2. So third one is 5. 4, 2, 3. A little bit quicker. Now everybody who had 325 should have gotten that one. That way. Who hasn't had 325 in here? Really?
Yeah, it's next year.
Well, it is. It's in the fall, but I would have. Is it only every other year?
Every 2 years.
Oh. Man, these semesters are going by like way too quick. Seems like I just taught that like not that long ago. Not quick for you?
No.
Oh.
4 minute
Well, I think that's a thing though. When as you get older, time goes by more quickly.
There's an actual formula for that? Those are sophomore.
Yeah.
I said there's an actual formula for that.
For how time goes by,
As you get older, time goes quicker.
like how much quicker? Like,
I don't know. Like we'd have to look at the formula.
well, you seem to know about this.
I know that.
I got that formula memorized. Tattooed on my back.
What's the name? What's the name of this formula?
I don't know. I can look at it.
Time goes by formula.
I don't think that's what as you get older.
Real.
Oh. Oh, internal time behaves as a square root of the age of a human.
Internal time as the square
So it
root
goes up exponentially.
of the age.
Yeah.
But then is that like the modifier? Like what does that tell me then? Just like
Age
square
is
root
the
of my age.
variable.
Okay.
Something.
But that doesn't tell me how much faster.
Well, yeah, it does.
So I just take the square root of so I take the square root of 20 and that's how fast time moves for me? Like what does that number mean for me?
All right, so square root of 38 is 6.16.
Like compare that to the square root of 20 and the difference is how much faster.
So 2 times.
2.
Or no, 2.
This probably has a percentage. So does time go by the slowest when you're 1? So it's everything's off of 1.
So years would be at their time by so slow when I was 1.
What's up?
Time went by so slow when I was 1.
I know. Seriously. Yenter finds it most convenient to chase the young bears. And did you see the movie that was it the Revenant. The
Yeah, that's what you were talking about.
yeah, man, he was
The bear.
looking at those baby bears. That shit, he shouldn't have been doing that. Is that mom bear got ticked, and that was the movie as a whole was difficult to. It was just boring, I thought. But the bear scene, it kind of played out like how you think a bear attack would actually go. It really seemed like that's what a bear would do. Just kind of throw you around a bunch and.
Guillermo del Toro said he spent like 2 years just studying bear attacks.
Studying bears attack.
Yeah, it's intense.
I know. I thought it was awesome. Although, you know what would have been really good? That was like, what, 15, 20 minutes into the movie? Something like that? If they literally would have killed DiCaprio. It's just like the last thing you expect. You don't expect like the main star of a movie to die that early, right?
Also because then you don't have a story to continue on.
But
Or
now
someone else becomes the main character.
no, but that's the thing is now the entire audience is like off balance.
You got Tom Hardy.
You're like, what the heck happened?
But then, the whole plot is about him trying to get back at Tom Hardy. So, just Tom Hardy living his life then.
You could just do this like a giant joke on the audience. So you kill off the star like really early in the movie, and then the whole rest of the movie like purposely doesn't make sense. It's like just about some guy fishing. And he's down there by the pond, and he's fishing. You're like waiting for like the movie to progress, and it never does.
Or you could just,
He heads back to get bait.
you
Keep waiting. They keep throwing in
or you could just
suspenseful
have him
music or
die,
something.
have the entire rest of the movie continue normally, except taking out all of his lines.
As if he's still there.
As if he's still there.
Right, yeah. They're talking to him.
Except there's no actor, there's no voice.
Do you have a little ghost that just kind of travels around?
No, there's no actor, there's no ghost, just everyone's talking to thin air.
All right, so questions on this one? Makes sense, the cool conversion. You can do the hex to octal. I think even Pebbles did it that way. See? Genius. Yeah, see? He learned something from it, too. It was like the only thing he learned was how to convert.
From any class? That's the only thing I remember.
He just finished up watching the lectures.
It's fresh in his mind. It's like, it's right there. All right, so that's that one. 3, what is universal I/O and how does it relate to POSIX? What I was looking for is something related to everything is a file. Okay, so you can say things like, well, you have the same functions, open, read, write, that's applicable to all the things, but at the end of the day, everything is treated as a file. That's why those functions work. Make sense? So, something along those lines. What are the 3 built-in file descriptors in POSIX-based operating systems? Standard in, standard out, standard error. Okay. I remember we did the redirects on the command line, and we did the little greater than sign 2 to redirect standard error. So those are the 3 file descriptors that are in every POSIX-based operating system. Write an error-free Hello World program in C. While we're at it, let's just see if, pun intended, vi hello.c. I just want to test something here. I gave people credit for it, but I want to know.
No, you don't even need to.
Oh, you can make a void?
No,
literally,
you
no,
can go
just
off main.
Oh, just main?
Yeah, it works.
All right, so you get a warning, but it'll still run.
Incorrect. Supposed to say hello world.
Take off points for
Just
that.
failed your own test.
Yeah, it's completely cool with that. What about cc hello.c? Yeah, I gave everybody credit as long as it was something something close, but you know, int argv or argc is the number of characters or number of command line parameters, and then char pointer argv is the actual string array of values. You know, that was probably what I was actually looking for, but you know, whatever. But the punchline is, you know, I do want you to understand what these command line arguments are for, because systems programming is very reliant on command line arguments. All right. So that was error-free hello world. Write a recursive factorial function in C. Many people made this way more difficult than it had to be. Asking you to write a recursive factorial function in C is the same thing as asking you to write a recursive factorial function in Java. It's the same syntax. Identical. All right, so we'll come down here. We'll say int fact, int n, if n is equal to 1, return 1, return n times fact n minus 1. Something along those lines. That's without the curly braces, but you know, same deal if you want to really spread it out some. And we could copy this function, paste it right into Eclipse, and it'll work just fine in Java. Same exact code. Whoa. Doobie doobie doo. This is supposed to be the CC one. That looks like it. Oh, there's your 24. All right. I'll throw that back up here for a second. Questions on that one? All right. Nobody should have missed that one, but a lot of people did. What is a race condition, and how do semaphores combat them? Okay, two parts to that question. First of all, race conditions. This is when more than one process is trying to access the same resource at the same time. And, you know, the final part of that of a race condition would be they both somehow gain access to the resource at the same time when only one of them should actually have control of the resource at one time. Okay? And this has to do with how resources are controlled. How we control access to them. So what's a semaphore? That's the second part of this. Semaphore is that specialized integer. It's a specialized integer that can atomically increment or decrement. And it counts up or counts down to lock the door, if you will, or another, the word we used in class was it's a bouncer, right? Protecting a particular resource. And that bouncer, because it's atomic, when those two processes come in, they have to go through that bouncer to get to to get to the resource. And because that bouncer is atomic, only one of them can possibly get through. All right, what does it mean for a operation to be atomic? Uninterruptible. It happens as if it's in one CPU cycle, something like that. So even if we have two things that are occurring at once, on a multi-CPU type machine, if it has to go through a semaphore, that semaphore will only let one through because it's atomic. That's the special nature of a semaphore. All right, so they're used to protect against race conditions. Now, something to keep in mind related to race conditions is we have these things all over the all over our operating system. So we probably have semaphores or other file locking type things all over the place to prevent more than one thing from saving a file before, making changes to a file and then saving it. Databases use these things constantly. So this whole idea of race conditions are very, very, very difficult to see, but are easy to, but they're all over the place. They happen all the time. So it's not really a rare occurrence. But it is difficult for us to create a race condition when we want one. Okay, let's see. What is the difference between a socket and a pipe? Give an example of when you would use each. All right, so a couple ways you can describe this. So for starters, pipes are unidirectional, sockets are bidirectional, but you can always create two pipes to create a bidirectional type of communication.
I thought named pipes were bidirectional.
By definition, they are. They create two separate pipes. They're implemented in terms of two unnamed pipes. So you didn't lose points if you didn't say unidirectional versus bidirectional, but that is a difference between pipes and sockets. Bigger difference is that sockets can communicate across a network, across multiple machines. Pipes are used for communication within a single machine. Certainly, and this even goes for named pipes. Named pipes are still communication can only happen in one direction at a time, where sockets can have two-way communication simultaneously. So that's still a difference between them, but not overly important. So the biggest thing is that sockets have communication across a network, whereas pipes can communicate within a single machine. Would it be a bad idea to just always use sockets and pretend that pipes don't exist? What would be the negative of that? So consider the implementation, how a socket versus a pipe might be implemented. Go ahead.
You're going to be using a lot more pipes because that's like local. So if you're using nothing but sockets, you might run out of sockets.
Okay, but let's think about the nature of a socket. So in class, we've been talking about pipes, right? We've been talking about how it creates a file descriptor and the operating system remembers the unique the inside and the outside of the input and the output side of the pipe, and they're just file descriptors, just like anything else. So we can read and write from a pipe in the same way we read and write from anything else, just universal I/O. So it seems like a pipe is fairly simple to implement. It's effectively a old-fashioned version of a singleton, right? We create a centralized place that we can say, I'm going to communicate through this. And now multiple guys can access that. How are sockets implemented? So when you consider this, a socket can't rely on that same sharing mechanism because the endpoint potentially is on a different machine. Okay, so if I'm one computer and Abe's another computer, I can communicate to him through his IP address, right? His IPv4, IPv6 IP address, and I'm making an internet connection over the network. Similarly, if I'm a process on a computer and Austin's a process on the same computer, nothing prohibits me from opening up a connection to the same computer on a different port. Okay, so sockets have one additional, this was something we haven't talked about in class yet, but something you guys read about, right? So when you read about sockets, sockets have, there's two pieces to establishing a communication with the socket. The destination address, okay, which is an IP address, or an unresolved host name, which then gets resolved by a DNS service. That's network stuff, not related to us in here. Well, maybe a little bit to us in here, but whatever. And then the port we're talking on. So this one computer sitting here, our modern operating systems probably have 2 billion, actually probably have 4 billion ports, because ports are probably implemented in terms of a 32-bit number. Historically, ports were implemented in terms of a 16-bit number. So you would have 65,536 unique ports. The first 1,024, 0 to 1 to 1023, were reserved for system stuff. So for instance, port 21 is FTP, port 23 is Telnet, port 80 is HTTP, that kind of stuff. But anything above 1,000, anything 1,024 and above was kind of fair game for our user level applications to use. So for instance, Austin can say, I'm going to listen on port 5,000. And I might listen on port 5001. And we're both running on the same computer. So we can establish a socket connection from my machine or from my process to his process on the same server, okay, but on different ports. That makes sense? Okay, so sockets have that additional level of communication. So when you consider sockets and pipes as being similar, they are similar in terms of what you use them for, but they're quite dissimilar when you think about their implementation. Pipes are very, very simple in terms of their implementation. It's effectively a singleton that we might use in one of our programming languages. A socket's a lot more complex. A socket is leveraging, the DNS servers. It's leveraging the TCP/IP protocol to unwind IP addresses. It's leveraging the operating system's port system itself to, so think about your operating system. What I'm calling ports is effectively, if you've ever seen like an old telephone switchboard, where back in the old days when they picked the phone and said, connect me to doc whatever, and you see the person creates the two connects a socket. All right, so you have your operating system has functional ports, and that port can only be used to if my process starts listening on port 5000, then nobody else can use port 5000 because it's currently in use. All right, so we do have a limited number of ports on an operating system, and we could take this a step farther and talk about denial of service attacks. Typically, so this becomes more of a hacking discussion. So have we talked about denial of service attacks in here, or just in other classes?
A little bit.
All right, so we have denial of service and distributed denial of service, DDoS. So this really has to do with bombarding a server with requests. All right, well, that's going to be really easy to do with sockets, because we could just say, I'm going to put it inside of an infinite loop, connect to google.com on port 80. Now we're hitting Google's web server socket. That's the HTTPD protocol, so it's between 0 and 1023, which are system reserved for POSIX-based operating systems. And we can just keep opening a connection to that over and over and over again. Well, it's very likely that Google's web server has some protections on it where they have reflexive access lists, and if they start noticing a abuse of incoming connections from the same source, they blacklist you or something. Well, what keeps me from actually bombarding Google's server on multiple ports? Forget about port 80. I'm going to hit port, port 1, port 2, port 3, just up and down, xylophone it, right? And we're going to keep getting disconnected because we're mostly going to get disconnected. We're mostly going to say, nothing's listening on there. So, for example, if I, let's just do the Telnet, localhost, pick your favorite 3-digit number.
666.
All right, we're unable to connect. It wasn't listening on there. Christian worldview. All right. Telnet, localhost. I don't think there's an HTTP server running on here. So here we're talking to Google's web server directly. So that is us talking directly to Google. But if we try to telnet to google.com on port, actually, let's see if they have a test server set up. Yeah, it's not. So it's trying to connect and it's going to get timed out. Well, if I have a multi-threaded application that just starts trying to open up ports to Google, I just keep doing that over and over and over again, Google might start thinking it's under attack. So in any case, sockets are significantly more complex than pipes are. So, the question I asked a few minutes ago was, why shouldn't we just always use sockets instead of, pipes? Because, sockets are certainly more modern, right? And than a pipe. So sockets are kind of the evolution of pipes, if you will. You know, they let you do everything you want to do with the pipe, but then also have some additional capabilities. Now, based on what we've explained and understanding that you haven't seen sockets at this point in here, that's kind of what we're coming up to next. We're going to be doing a chat server. But since we haven't seen sockets yet, would you say that setting up a pipe is pretty trivial? It's 2 lines of code and we're done, right? You don't even think about it. We don't have to worry about sharing the communication or anything like that because it's the operating system that's managing the communication. The buck has been passed. Whereas when we're using sockets, we have to do more work ourselves. One of the 2 sides is set up as the server, the other one is set up as the client, so we're creating our own protocols rather than leveraging the existing operating system. So there are examples when a pipe lets us do what we need to do in a couple of lines of code, where a socket would be far more complex to work with, although it would certainly do what we need it to do. So there's a good reason not to just always use sockets. That's probably a better answer than saying that sockets take up too many system resources or something, because for normal software applications where we're just communicating between a couple of processes to use a socket, we're probably not going to run out of ports on our computer. You know, the idea of translating between an IP address and a local port, this is not taking up tons and tons of system resources by today's standards, so that's not really a problem. All right, so for that particular one, something along the lines of sockets support external communication between multiple machines, and pipes are only on a single machine. That kind of stuff. Okay, also keep in mind there are 2 sides to that question. The first one is what's the difference? The second one was give an example of when you would use each. Okay, so socket, you might say like a chat server. You know, where a pipe might be used for a, you know, maybe even use our merge sort example or something like that, where to communicate back to the parent.
Which we still haven't
Maybe we still haven't finished it.
finished. Merge sort.
You mean in class? That's true. I still stand by the fact that I could definitely do it in class.
I don't know about that.
All right, keep thinking that.
Okay.
What is IPC? Why is IPC needed in relation to the fork system call? So IPC is interprocess communication. So this is our, you know, this is a descriptive mechanism that's facilitated through multiple system calls in our POSIX operating systems that allow multiple processes to talk to each other. Why do we need it with the fork system call? Because the fork system call creates new processes, and those processes might be interested in discussing things with each other. So that would be fair game, right? Let's see. Why would using universal I/O to read a file 1 byte at a time into a 1 byte buffer and display the byte to the screen be extremely inefficient? All right, so multiple parts to this. So for starters, if we're using universal I/O to read stuff in, we're treating everything as a file. We've dealt with this in class a bunch of times when we have our little string buffer, and we're going to decide that the most we're going to allow us to read in at a time is 1 byte. All right, so right off the bat we can say, well, since we can certainly read in more than 1 byte at a time, and universal I/O seems to indicate that, well, universal I/O's functions, the read and write functions, allow us to specify the maximum number of bytes read. But read also returns the actual number of bytes read. So we don't have to worry about our data being evenly divisible by our maximum number of bytes. We can read chunks of 100 bytes, and on the very last read we get 3 bytes. That's legitimate. Right? So reading 1 byte at a time seems to be inefficient from the perspective of how does our how do those system calls actually work? You know, how do we read something in from a file 1 byte at a time? All right, so first of all, we got to think about nature of file I/O. File I/O in and of itself is very slow. So when we read something in from a file, that is an I/O operation. So when our process is running through the CPU, and the CPU finally gets to the part of the process that says read something from the file, it then needs to interrupt the process, causing a context switch. So kind of a key phrase I was looking for there is the context switch phrase. You know, understanding that context switching is the real enemy into why this would be a bad idea. So we're context switching when we actually read in the byte from the file. Then we're going, so now we have the byte. Now we're getting back in line for the CPU, going back into the CPU, only to then get interrupted from the CPU again, because we need to write that out to the screen, which is also I/O. Okay, we've seen the examples of our programs where if we try to print out 100,000 numbers versus count 100,000, sum up 100,000 numbers, it's a very different amount of time that we experience, right? So because I/O is expensive. File I/O is more expensive than screen I/O, but they're both very expensive, and they both come with context switching attached. So now for each byte of that file, we're context switching 4 times. Okay, 1 time into the CPU, 1 time out of the CPU, a 3rd time into the CPU, a 2nd time into the CPU, a 2nd time out of the CPU, for a total of 4 context switches to read a byte and write a byte. That make sense? So lots and lots and lots and lots and lots of context switching, and there isn't a real advantage to being able to get things 1 byte at a time. Except we did an example in class where getting things 1 byte at a time was advantageous. What was the example we used in class to get things that we got things 1 byte at a time where it was advantageous? One of our first assignments.
Writing it in reverse.
Yeah, reversing a file. We read in a file and we reversed it. Because of the nature of that, because we don't know how to, at that point, I guess we still technically haven't done it. We haven't built up our own strings. We didn't have the ability to concatenate and manipulate strings. So when you consider that, think about how helpful Java is. When we first teach Java, we talk about Java being a string-based language, and it's really easy to build up strings and manipulate strings and things like that. And look at an older language like C, and also C++ suffered from this as well until it introduced a standard template library, which brought us C strings and then even some other string libraries. But working with strings was not easy in those older languages. It wasn't a friendly thing, and we take it for granted with Java. All right, so questions about that? Question about the exam? Everybody should have gotten 100. Only I think 2 people did. Low grade was a 10. There was a couple of 20s. I think class average was maybe an 80 or 75, something like that. So class average wasn't horrible, but there were some pretty embarrassing grades. So you guys should be ashamed. If you're the one who got the 10, I'm not looking at anybody individual. No, he didn't get it. Chastity's off the hook. Yeah, you might want to rethink life. Maybe go into basket weaving or underwater basket weaving.
No, you got the conversion question right. That's at least 10 points.
That's the only time.
Yeah, she did all right. Yeah, so just yesterday, the underwater basket weaving. I taught Dover yesterday that there's a real sport, underwater hockey. It's a thing.
What?
Yeah, you're gonna check this out. They're trying to get into the Olympics.
Do they have oxygen tanks and stuff?
Nah, it's hardcore. It's just
No,
so you can just hold someone down and kill them if you really don't like them. It's a red card though. So.
Upside down.
What? You don't have sticks though, do you?
They're these little.
It's like so it's like Neil
So it's a
hockey
kiddie
sticks.
pool.
See? What's up?
I messed up my exam. It was not.
Oh, you're working on the exam now?
Yeah, I just started it. I replayed the page.
All right, I'll come down and check it out here in a minute. We're just finishing up.
Sorry.
Yep. All right, yeah. So this is underwater hockey.
So is the puck weighted?
Well, I would hope so.
I think the puck is
You
probably
know,
waiting.
you have to fight against
So
it
it's
too.
staying at the bottom of the
It's
pool.
probably like a actual hockey puck.
How do you check someone? Is
It
there
might
still
weigh a little
icing?
bit less, but
What's this?
I said, how do you check someone? Is there still icing?
I don't know.
You can underwater splash.
It'd be funny if there was like some sharks swimming around back here.
Probably
Yeah.
similar to water polo, honestly.
You get sharks swimming around back here. You got some dude up on the surface chumming the water. how do you make underwater hockey extreme? They introduce sharks into the pool and
At the half, they put one in.
what's this?
I said at the half they put one in, and then if it goes into overtime, they put.
Oh yeah, I got you. You introduce additional sharks. And-
the puck is no longer a puck; it's a steak.
Well, that's why I'm having them chum the water. That's the chopped up fish.
Yeah, but you gotta have some. You gotta have some excitement to the puck, though.
Yeah, see, I always thought that would be interesting if they did that in that Survivor show. See, when the very first series episode of Survivor that came out, which might have been before some of you were born, you know, everybody was like in like tuxedos and because they didn't know they were going to get dumped on some island. Well, now everybody knows they're getting dumped on a tropical island, right? So they're in, you know, bathing suits and stuff like that. Well, it'd be funny if they just, well, I've joked if they dumped them in Antarctica and just say survive and 10-minute show. They're in a bikini and it's negative 113 degrees. You know, but what if you just dumped them in the middle of the ocean? I mean, like nowhere near land. Okay, so they're out there in the middle of the ocean. You throw one of these, rafts down there, and then so they're all trying to climb into the raft, and then you start chumming the water from the helicopter.
It has a slow leak too.
You have on the raft, yeah, it's a slow leak, and then there's also like a container on there with like a timer, and probably 15 minutes in for the current survivors, it blows up and everybody's covered in monkey blood, and then the raft separates, and now you're in the water again, and it's probably the frenziest slow down from the chum now. So now we've introduced new bait. So just saying that would be a good idea.
Pitch that one to HBO yet? It's pretty developed.
I don't think they'll quite accept that in the United States, but you can probably take that to China.
Well, same thing with like if you had, like I don't understand. You can fill us in on this. So I don't even understand the hunting stuff. So, you watch these hunting shows and find it's interesting enough. But when you're sitting in a tree, covered in camouflage with a rifle, and a deer's just wandering by, like just minding its own business, and all of a sudden it gets shot in the face. How is that even fair? Let's go out into the African. Let's go out to the African. Just.
You get a rhino chasing you.
No. What we're gonna do is it's gonna be just one human. You're gonna cover him with monkey blood. Okay. He's gonna a sharpened stick. Okay.
I'm pretty sure that's happening in
Okay.
Africa right now.
Right. Exactly. And then there's a lion. Go. Okay. That's what's gonna happen.
Lion King.
Don't turn away. Don't turn away. Now, if you wanted it to get more interesting, you don't want it to be a big open field. You want to get them in a nice confined,
Room
yeah,
like this size.
this size room.
Not too big.
Get a lion, a bear, and a dude with a sharpened stick.
Why don't we just remove the ceiling and put bleachers around while we're at it?
That's what I'm thinking. Now, the messed up thing is, people would watch that show. Absolutely, they'd watch it. All right, so the next time we meet is a week from today.
Seems that way?
Yeah.
We don't have class Friday. We don't have class Monday.
Yeah.
All right. Yeah, apparently not. Right?
After 4. Classes after 4.
So it's just,
So I'll see you Monday.
yeah.
Yeah, we'll still see.
Yeah, you'll see me Monday. All right, so I will see you on Wednesday.